Hi, this is an introduction to parametric equations. It's our next topic that we're going to be studying. If you need to look anything up as a reference, check in section 9.4 of your textbook. Parametric equations are something we haven't studied before. In Algebra 1 and Algebra 2, we study equations in terms of x and y. Parametric equations introduces a third variable into the equation, and that is a variable of time. The great thing about it is it lets us graph things in our calculator that we couldn't graph before. So we can actually graph the ellipses and the hyperbolas that we studied in the last lesson, as well as those sideways parabolas, all of those quadratic functions that are not, quadratic relationships that are not functions. So, what is a parametric equation? Well, up until now, we have graphed a single equation involving two variables, just x and y. So we could have something in terms of x and y, and we would use the equations to describe implicitly in terms of x, meaning we would solve for y, and everything over here would be in terms of x. We could also use the equations to describe implicitly in terms of y, meaning that we would solve for x, and everything over here would be in terms of y. Parametric equations introduce a third variable to this relationship, and this relationship with this third variable cause a curve in the plane to happen. And the third variable is t, or time, and that's what we call our parameter. Before parametric equations, an equation such as a parabolic curve would tell where the object has been. It doesn't tell when the object is at a certain place or a certain xy point on the graph. Parametric equations allow us to actually graph the complete position of an object over a set period of time. So the formal definition, if f and g are continuous functions of t on an interval I, the set of ordered pairs f of t and g of t is a plane curve C. And that means you're going to have equations x equals f of t and y equals to g of t. That's two different equations. Notice both of those equations have that component of time here and here. So it takes both of those equations to make the curve. And that t that's in both of those equations is called our parameter. So there are two types of parametric applications that we tend to look at. The first one is circular motion. So think of a Ferris wheel and how a Ferris wheel moves. The graph could represent the position of a point on the Ferris wheel. We could find information like the height off the ground, or the direction, or the speed of the spinning wheel. So there's a lot of things that can come into play when you add that motion into the problem. The second common real-life situation is projectile motion. And where we did do projectile motion in Algebra 2, we're going to talk about it in a little different terms with parametric equations. So think of x as the horizontal vector, or that horizontal line here, and think of y as the distance from the ground up to the sky, so a vertical vector, since we just finished studying vectors. And so that result of those two things would be at this point. So the resultant would be right here. Now, what that point is actually representing, though, is a place on the curve. And so what happens then is when we add time, then we're talking about this object moving along the curve, along the curve, along the curve, until it gets to this point that is this horizontal distance and this vertical distance, and now we'll be able to calculate the time with which it takes that to happen. So for instance, think about kicking a soccer ball, where t is the seconds and the distance are in feet. So the horizontal distance and the vertical distance are in feet, and the time on the curve is in seconds. So we could actually find at what time the ball reaches its maximum height, instead of like we did in Algebra 2, where it is when the ball is here, what is the maximum height. So we can actually find the time that it takes for that to occur. So that's kind of cool. You're going to look at your calculator and notice that it's going to be very different looking when we're in parametric equations. So to be in parametric equations, we need to change our mode screen. So if you press the mode button, it brings up this screen, and then we arrow down right here where it says function. That's what's normally highlighted. So we're going to arrow over and select parametric and then hit enter. And so when we do that and we press the y equals button, we get a screen that looks like this. So it's not y1, y2, y3 down to y10. It's x1t, y1t, and those two equations together make the curve on the plane. And we could do x2t, y2t, so that would be a second curve on the plane. You can still arrow back on top of this line back here and change how it graphs, so you can have dots, you can have thick line, you can have a normal line, you can have a line with a trail, you could have just the motion, so there's lots of things you can do to change it there. When you press the window button, you're going to see the window looks different as well. You have t-min, t-max, t-step, you have x-min, x-max, x-scale, and y-min, y-max, y-scale. So the x-min to the y-scale is just like it is normally in an equation. You're talking about how much do you want to see horizontally for the x's and how do you want to see that plotted, and then you're going to do vertically on the y's and how do you see that and how do you want to see that plotted with your y-scale. But now we have this t-min, t-max, t-step, which is all dealing with that third variable of time. So the minimum time to the maximum time, and how are we going to keep track of that time as we go along. So the beauty of this is by being able to represent the curve as two lines and that motion with it, that we can actually graph things that aren't functions. So we could graph conic sections and all kinds of stuff like that. So what do the t-values affect? Well, in this t-value right here is what I'm talking about, t-min, t-max. That is going to affect how much of the graph you see. In other words, it's the time being graphed by the equation. What does the t-step affect? The t-step is this piece right here, and that affects how frequently the points are graphed on that time increment. So the further the t-step is apart, the flatter. There are going to be little flat lines moving around your graph. The closer they get together, the less of that you see. You see more of the natural curve. So basically, as the general rule of thumb, the smaller your step is, the more accurate your graph is going to be. The drawback is that the steps get smaller and your calculator takes much longer to calculate and to graph your parametric equations because it's graphing more points. So as a general rule of thumb, the default value of the t-step is usually a good balance between graph accuracy and the time it takes to graph. So sometimes you might have to play around with that t-step to get a decent graph that you can see. And when you graph them on your calculator, you're going to see the motion as it's happening. So that's just kind of a basic overview. Play with your calculator a little bit, make sure you're comfortable with the settings and how to get in the mode and how to change the mode back out, because we're going to be using it on our notes for the next section, which is parametric equations day 1. We're going to learn how to graph them, how to go between rectangular equations and parametric equations, what has to be a part of your graph, how you get the graph, and we're going to rely on a lot of the graph knowledge that we built in Algebra 2 to help us do that. So we're all going to kind of pull some of this together in the next section. So this was just a brief taste of what we're getting ready to do for the next 2 days, Parametrics Day 1 and Parametrics Day 2. Thanks so much, guys. Talk to you next time.